Thanks again. Thank you for coming in spite of the hurricane, the waves, and our possible death. Imminent. But we will see it in as a first starring role. So, glad to join you here, and thanks to the organizers for having a great time here. And we've had great talks and scientific discussion. So I would like to switch to a different subject this afternoon. We've been talking about particles. Today we discuss more about nanoclusters and nanoparticles, all that kind of systems. And now I will be switching to the opposite. I will talk about nanopores, sorry. My English is not so good at this in the siesta time. So what I will tell you about is how we work in mesoporous materials, which are very interesting materials from the point of view of applied technologies, but also there are very interesting implications in basic science. I will in particular discuss how to make some mesoporous materials, which are strategies to build them, and also how to use these mesopore systems, which are nanoscopic channels that have very interesting properties due to confinement, due to the limited size of the pores, but also due to interactions that molecules have with these pores in the controlled transport of molecules, for example, of reactants, of hormones, everything. So, and I will particularly emphasize on how to make membranes that permit to exclude some molecules while pre-concentrating or permitting other molecules to move around. So this will be more or less my presentation today. So I come from Buenos Aires, Argentina. It's quite far away. Somehow the antivirus tells me that I'm protected. Good, very nice, but let me go on a presentation. We are in Buenos Aires. This is Latin America. This is Argentina, Buenos Aires. And I belong to a young, thriving university, University of San Martin, founded 25 years ago. That is just in the outskirts of Buenos Aires. We have a very nice campus. And since 2015, I've been putting up an institute called Institute of Nanosystems, because we ran out of the words nanotechnology and nanoscience, so we had to go to nanosystems, and we were interested in nanosystems, as you will see. And we are basing our institute in simple principles. We are interdisciplinary, we try to be international. Now we have, for example, this second semester, 9 of our people are in laboratories all around the world. And of course, we are adopting an interesting scheme. We have small groups with very young researchers with experience abroad. Meet them here, and the subjects are very diverse, but they are centered in knowing how to make your nanomaterials and knowing how to use them in particular problems of biology, problems of environment, problems, for example, of prosthetics, medicine, etc. So if you're interested, you can visit our site, our media, etc. Well, today I will not talk about only nanomaterials, but I would like to go a little bit forward to talk about nanosystems. And what's a nanosystem? It's a system. We can define a nanosystem as these small partitions of matter, for example, that exists in living organisms. If you analyze these very schematics of a cell, I know you on the back will not see anything, will not read anything, imagine, but it's okay. If you see a cell, you see that here are processes that take place very carefully, very efficiently, and in a very specialized way into small pockets or domains. And that these domains coexist, and that this coexistence also is turned on and off by different signals. So here, a living organism, it's an example of what a system composed of smaller nanosystems can behave. And the complexity is an emergent complexity that is due to the existence of all these pockets and all the interactions between them. So can we make this? Can we make this from the basic nanotechnology point of view? And we design systems in which, for example, we can give one part, we can print in one part of the system a given heating element, and then, for example, transducing information in the shape of heat, of light, of molecular conformation to another region, for the other region to make a second actuation. Can we do that? Sure we can. We know a lot about how to make nanomaterials. We know a lot which are the properties of these nanomaterials, and we surely will know how to link these properties in order for these nanospecies to collaborate. When these species collaborate, the overall task is better than the sum of the two parts. So this is what's called emergent properties. You get more of your system by making parts of your system collaborate among them. So I will try to show you some materials that in a very primitive way they are doing this kind of concerted work together. We'll try to give you that idea this afternoon. If the waves permit. Oh no! Nah, don't look. Don't look, it's better to die without no. So I structured in more or less three parts. In the first part, I will show you how to make these mesoporous materials, which are matrices, which are architectures that are very controlled, in which you can control a lot of different properties with very few synthetic steps. Of course, if you know how to do it. And if you want, and now after 20 years of working in this field, or 25 years that this field has developed, there is a rational approach in order to be able to pre-design material. I will show you how to think about this. Then, after the architecture, of course, we build the architecture, then we decorate. We build the furniture inside. So we program properties by populating these rooms and these walls with the appropriate furniture, pictures, tables, etc. And then, finally, I will show you how to combine these properties, and now we are lucky because we can rain, in order to create systems that begin to show some responsibility and maybe some programmability, in the sense of we can design the system to do a performed task, a previously thought or designed task, and we can program the response of this material by carefully tailoring what's happening inside, for example, these pores or these pores. So this will be the line of my talk. Of course, I'm a synthetic chemist by training. Who's a synthetic chemist here? Two? Nah, come on, don't be shy. Okay, who's a physicist? Engineer? What are the rest of you doing? Any chemist. Today is the mole day. Mole day. 10:23, 6:02, from 6:02 a.m. to 6:02 p.m. we are the mole day. So other chemists. Good. So I will try to show you how to use tools from chemistry, from physics, from biology to try to get to these intelligent systems. Being a synthetic chemist by training, I browsed the very old literature and found this very inspiring fragment from Marcelin Berthelot, one of the best old books you can read, along with Lavoisier's memoirs, La Synthèse Chimique. And I rescued this paragraph. Berthelot is known because he's one of the founding fathers of synthetic chemistry, if not the founding father. And here he says, we can hope to recreate all the substances that can be developed since the very beginning, tabula rasa, from zero, by using the forces that nature puts into action to make these palm trees, rocks, whatever. And what are the forces we are using? I agree with that. And what are the forces and the processes we use? Well, what we can do at present is to make building blocks. We have seen exquisitely designed building blocks yesterday and today in the morning. These clusters, these nanoparticles, these thin fields. We will see probably exquisitely designed polymers and molecules, molecular design. So these are building blocks, and the interactions between these building blocks are also very important. If we know how to tune and tailor the interactions between these building blocks, these are forces of nature, and if these forces lead us to spontaneous processes, we have what's called self-assembly processes. Self-assembly between building blocks of different size, shape, and interactions. This self-assembly is known because of self-assembly of like molecules, but you can do with different molecules and different building blocks, as I will show you in a couple of slides. We can take a lot of advantage, all the chemists, to use orthogonal reactions. Which are orthogonal reactions? Are reactions that produce in one site or in one particular site or with a particular atom and not with others. Why? Because we can select where to make a particle grow, where to sit down a particle, where to begin making a brush polymer. So these sets of orthogonal reactions are an essential building block if we want to control not only what we do, but where do we put it, because we want to be like nature. Finally, we can couple all the properties. If you, for example, think about one building block, one titanium dioxide small building block, one gold cluster. Yesterday and this morning, you saw that there were critical sizes in which some optical and electronic properties appeared, and that could be tuned by very finely tuning the size, for example. But these properties were shown very, very well this morning that were dependent on the interactions of the very cluster with the ligands or with the nearby surface. So by tuning position, by tuning vicinity, you can tune the properties. And you can couple optical with chemical properties, optical with local properties. Think about excitations, think about enhancement of fields. You have a plethora of things to work with by combining size, shape, local fields, optics, magnetics, etc. So we have a playground to research for hundreds of years. Of course, if the waves permit. So, I will talk about mesoporous materials in the rest of my talk. And this is a pack of micelles, which are packed. A micelle is a nanoscopic object, per se. It's a self-assembly of molecules that, in this case, parts the space into a hydrophobic interior and a hydrophilic exterior. You can concentrate these micelles, for example, by precipitating, by making a liquid crystal, and you part the space, and you can make sol-gel chemistry. Sol-gel chemistry is very mysterious, don't worry, it can be done, but essentially it's inorganic polymerization. And if you are able, for example, to make an inorganic or an organic polymer in the hydrophilic region of this space, you end up with this kind of fossil structure, in which you have the micelles trapped into a second phase you form. For example, you precipitate silicon dioxide there. Or you make a polymer, and then you carbonize it. Then you burn away these micelles, and you end up with this kind of material, in which the micelles acted like a template, and a template for pores. And these pores are called mesopores. Why? Because they are pores in the middle length scale between micropores, 2 nanometers, the smaller size, to macropores, from 50 nanometers on. So we will deal with materials having pores between 2 and 50 nanometers. Making such small pores is very interesting from the point of view of having a high surface area, because a silica with 4 nanometer diameter pores presents more or less 900 square meters per gram. Silica, carbon with 6 nanometer pores diameter presents 2,000 square meters per gram. So they are very high surface area. But this, spurred a lot of interest in catalysis, in the field of catalysis, and in separation. I will show you that there is more to mesopores than just high surface area and control pore size. There is monodispersity. Each of these pores comes from a unique micelle. So they're totally monodispersed, and they're very interesting. Because if all the electronic properties of nanoparticles derive from their size and shape, and you have an effect on the size in the confinement of electrons, here you can confine solvents, you can confine molecules, and change totally the behavior. You change the thermodynamics and you change the kinetics. Okay, but there are lots of fields of applications for these materials. I will not discuss them today. Just let me tell you that in a very few synthetic steps, one well-done precipitation, one calcination, that's it. One film deposition, treatment, and then thermal treatment to eliminate the surfactant. But you can create a very complex material in which you can tailor what happens at the walls. For example, if the walls are crystalline, if they are nanocrystalline, which is the crystallite size, which is the phase, which is the composition. Just one synthesis step. Of course, you have to know what to do, but this is not. And then you can also change the pore structure. You can make sponges with very, very highly tunable pore systems. You can control the pore diameter, the neck diameter, you can control the surface, you can control interfaces here, and you can, of course, sit molecules on top of these surfaces or populate the pore interiors. So you can do a lot of a huge variety of different systems which are very complex in just few synthetic steps. Why is people dedicated to mesopore materials? Mesoporous materials are very proud of controlling the pores and controlling organization between the pores and seeing if we have really beautiful materials and very controlled materials. And why is it so important? I will dedicate this talk to control molecular transport, but let me show you very briefly two very interesting effects that have been recently the community has been recently working on, which is solvent confinement and nanotextures on the surface. And of course, you have a lot of implications about having controlled surface area and controlled pore size. Let me show you this. This is a couple of recent works we did, in which we saw solvent confinement here. This is a simulation experiment we did in collaboration with theoretical people, and we made a systematic study of what happened when water, which is a quite complex molecule for an absorption processes, absorbs into a 3 nanometer mesopore. 3 nanometers, to give you an idea, is 10 times the diameter of water. So side to side you have 10 water molecules inside a pore. This is the density, computed density. We made a molecular dynamics experiments, and you see the computed density here from the pore center to the pore edge. And what you see here in the blue and red curves, which are here, is that when you have very little water in contact with this material, the water absorbs on the walls. But there's something very interesting here. There is a structuring of water on the pore walls. This is due to the very intense interactions of the oxide walls. This is a titanium dioxide, and this is water. So the surface is polar, water is polar. It absorbs on the surface, it creates a first layer on the edge, a second layer, and then when you fill the pore with water, you have liquid water here, but not along all the pore. You have liquid water in the center of the pore, and you retrieve a density of 1 here, but then you retrieve also the structuring of the water here on the walls, and then you have some structuring here. This is the density of water. See these fluctuations. This means that you have some structuration of the water. So the water is not continuously liquid inside a vessel. We measured this also by relaxation NMR. So we could observe that there is a very peculiar and size-dependent story of water here that, for example, has implications in catalysis, in flux, nanofluidics, etc. Another interesting and rather unexpected thing happened to us when we wanted to use these mesoporous materials in the shape of films. I will show you later the characterization more closely. What you see here in the back is an atomic force microscopy. You see the pores here, and you see the walls, and you generate these patterns on a surface. And when we wanted to use these as for cell culture, because we believed that if we put, for example, any kind of molecules of pharmaceutical interest inside these pores, like antimicrobians or like growth hormones, we could induce changes in the behavior of cells that were growing onto this kind of substrate modified with mesoporous materials. What we found was much interesting just with the blank experiment. Without putting anything in the pores, we found out that the growth and proliferation of cells, osteoblast cells, which are the cells that eventually form bone, significantly changed by changing the porosity. This means that cells look at the floor, and if the floor has a pattern, like the floor here, the cells are not so sure to grow there. Porosity influences cell growth. We saw this also with bacteria. Bacteria, for example, Pseudomonas aeruginosa, which is a bacterium that forms biofilms, which is a very nasty way to colonize a surface, which is dangerous in hospitals and bad for industry. Bacteria develop biofilms on surfaces, but when you pattern the surface with this kind of mesoporous film, depending on the pore size, bacteria do not create these biofilms anymore, keep isolated, live their life isolated, and die easily. So this is nice, because you can give a physical signal to a bacterial colony in order to tell the bacterial colony, no parking here. So these are two aspects I wanted to emphasize. We can control, for example, the growth of cells and bacteria just with a physical cue, with a physical signal. And the other one, we have very interesting effects that we still need to understand and exploit for a bunch of applications, such as, for example, catalysis or nanofluidics, due to only to confinement. Okay, I will show you very briefly in the rest of my talk how do we make mesoporous materials, how do we modify them, and some examples on how we use these modified systems to control flux of molecules. The first I will discuss is to make mesoporous materials through a particular route called evaporation-induced self-assembly. Evaporation-induced self-assembly is just a very, very versatile route put up by Jeff Brinker in 1999 that coined the name. It's a very simple and very effective route to make mesoporous materials very easy. How do we make this? For example, this is a picture of a titanium dioxide film. On a substrate, you see here a change of color. This color is a color of interference because the film is thin. This is a variation of color because it has some 10 nanometer variation in the thickness. It's a drop effect. Anyway, we can do continuous films by using solutions, by deep coating or spin coating or spray coating or casting, just a method of depositing a solution onto a surface and letting dry. And in these solutions, we put inorganic precursor, in this case, titanium precursors. Then we use surfactant. This surfactant is particular, it's a polymeric surfactant, it's a non-ionic block copolymer. It's a polymer with 3 blocks, hydrophilic, hydrophobic, hydrophilic. Can be tailored by tuning this, can be bought from several providers. And by changing the N, this is very nice, it was discovered by several researchers, Wisner and Stucky groups, 20 years ago, more or less. But by changing the N, the polymerization, the polymer length of this, you can go from spherical micelles to tubular micelles to very intricate designs. And you can vary, of course, the size of the molecule and then the size of the micelle very easily. And then you can control the mesopore cycles. So, how do we do these materials? We have this magic solution. It takes a couple of months to be trained in how to prepare the solution with an organic volatile solvent like alcohol, a little water, the inorganic precursor, the core template, mix everything like a good chemist. Then you deposit a thin film either by dip or spin coating. I will tell you then the process of film formation. A film forms, and eventually the micelles get into place with the inorganics. You obtain this called mesostructure material. It has a structure, it has the micelles, and you have inorganic all around, not totally condensed. It's like a gel. Then you heat up this, you consolidate the inorganic framework, and you remove the template, the molecules, and you get finally to your porous oxide with the desired receptor. This is just one example. There are several thousands of examples. This is a picture of a film. You see that it's thin, that it has very good optical quality. This is a cross-section, transmission electron microscopy. You can see the pores. The pores are very organized. They're all equal and organized in space and well-oriented. We see this by transmission electron microscopy, but if you shine an X-ray, if you shine X-rays here, there is diffraction. There is diffraction at low angle. Why? Because you have periodicity in the electronic structure here, the walls, in the electronic density, you have periodicity here, and this periodicity is in the order of nanometers. So you have diffraction at low angles. And by identifying the spots here, and by indexing, you can, for example, retrieve all the symmetry of this network. And we know how to do it, and we spend a lot of time trying to understand what's happening. But now we are sure. This is scanning electron microscopy. You see here the surface of such a film. You see the pores, which are regularly oriented. You see maybe some domains. These pores are in this domain, these pores maybe in this domain. See domains here. But globally, what a cell sees when it's landing there is, oh, there are craters at 4 nanometer distances, or 12 nanometers, or 9. We will have a different behavior because the proteins will have a different interaction with that surface. So we can determine very well the porosity here by using absorption and desorption. But desorption and desorption can be done optically using, for example, ellipsometry. So you can get a very, very precise information. We spent several years trying to understand how these things formed. And to make a long story short, this is a kind of ballet. You know ballet? This is a dilute solution. The substrate enters here, and when you pull the substrate outside the solution, you form a liquid film. The liquid film begins to evaporate because there is a volatile solvent. Micelles begin to form, micelles begin to pile up, and eventually form an organized lyotropic structure, lyotropic liquid crystal, with some organization. The image we have in our heads after doing hundreds of experiments in synchrotron, using different techniques, will take a long time. Remember, short story, was this. When we created this mesostructure material, we had organized micelles, and these organized micelles were surrounded by small and very hydrophilic inorganic species. We worked with this with several years, and more or less the lesson was make small clusters and let them organize, because you should maximize the favorable interactions between these hydrophilic clusters and the hydrophilic exterior of these micelles. What we did, But we didn't have any quantitative way to understand what was happening. Until a couple of years ago, which we began working with Markus Müller group. Markus Müller is an expert in phase separation of polymers from the theoretical point of view, and Chi-Yun Tan was his postdoc, very talented scientists that helped us to understand the problem. We needed to work with the theoreticians. And this is very nice because yesterday we saw and this morning we saw fantastic talks about an important trend in nanoscience today. Theoreticians and experimentalists should work together because the work is much better when we work together. We understand. So what we told Markus and Chi-Yun was we have a template which is a polymer, and this polymer may interact with small entities, small colloidal entities. And immediately they thought, okay, a colloidal entity is a particle with a diameter, with a potential. This is physicists. Particle, attractive potential, repulsive potential. Polymer, attractive with particle, repulsive, Q, entropy. They created a simulation, a theory, coarse-grained theory, simulations, and they permitted us, by varying the potentials, I won't go into details, by varying the potentials and by varying the size of the polymers and the size of the building blocks, in the first work, they arrived to explain very old results that we didn't understand why happened. We had some fancy chemist explanation with the fingers. Oh yes, polymers go like this. No, they make the numbers and they arrive to the real numbers. So they say, wow, this is powerful. And we went one step beyond. We said, can we use preformed inorganic building blocks and then make a self-assembly predicted by theory? So we worked in collaboration with the Japanese group, Masaide Takahashi in Osaka. They developed this very nice synthesis of very small nanoparticles that have a layered hydroxide structure. And we went to synchrotron in order to know exactly in which conditions we could prepare small nanoparticles from 2 to 50 nanometer diameter, and tested all the conditions. And it works. Taking first the theory and trying to adapt and cross the data from theory regarding, for example, which is the optimal size that interact with the polymer and the conditions and the post-treatment. It's a very robust and interesting theory. We were able to develop a lot of different materials just by using inorganic building blocks as the source, preformed, no reaction. Then we studied a little more this system. This is nickel hydroxide, for example, and we made a feedback. Very interesting. Yesterday, one of the speakers talked about the importance of feedback between theory and experiment. This was fundamental because the potentials are the potentials. But if you don't have experimental data, you cannot refine your potentials. And you can refine your potentials, you are much nearer truth. And what we saw in the case, for example, of nickel hydroxide, is that when we use nano building blocks that were smaller than, say, 4 nanometers, the theory would predict, with all the optimized potentials, that we have a very good organization. This is patterns of organization obtained by theory. This is Fourier transforms. This is what we obtained from experiments. And for larger nanoparticles, the system will not give an order. Pattern. We tried this at the synchrotron. We isolated 4 nanometer particle of nickel hydroxide. We isolated them, we mixed them, and the experiment sometimes is right. These two guys are very happy, seeing that effectively we predicted an organized system and we got it. This is the moment in which you have the good success. Okay, with this approach, the same approach, now more quantitative, we can tailor matter not only in form of thin films, but in hierarchical porous monoliths, films with double porosity, very well tailored, combining different methods, nanoparticles by using aerosol system, etc. Now let me talk a little bit in the last minutes of the talk about transport. Now, in the first part, I show you how we make the materials, how we control the materials, how we control porosity. Now, let me show you and let me ask you, how do you imagine a molecule will move in these systems? How do you make nanofluidics here? Nanofluidics is a dirty thing. It's very complex. Why? Because the walls are very close. And the sizes of the nanofluidics are the sizes of the molecule, or an order of magnitude more. Imagine you moving here, you're very happy. But imagine we get the walls closer, like in Star Wars. Imagine an aisle in which you have to move among the crowd. Effects of the walls, effects of the people. What happens to a molecule that comes from, that exits one pore and enters the following pore? One molecule here has to pass here, and it has a definite size. It has a solvation layer, and it also has interactions with the walls, but the walls are not just the walls. You have solutions there. And the walls might be charged. The walls might be involved in adsorption equilibrium, and also the walls can have a double layer belonging to salts solution. So the problem is quite complex. The problem of moving this molecule from here to here. Let me show you a couple of experiments in which you can use to assess the movement of the molecules. One is electrochemistry. It was shown this morning, for example, in the case of catalysis. You can have an electrode, you can cover an electrode with a mesoporous thin film, and you obtain this kind of signals during cyclic voltammetry. Maybe you are familiar with it, maybe not, but here what the deal of this is taking a molecule that will eventually diffuse to an electrode and give or take one electron. You change the potential and you record current. And if you have oxidation or reduction, you will record it as a current in the oxidation on or in the reaction cycles. What you see here is one molecule that is crossing or not this mesoporous film. What you can see in the blue curve is a typical response of a system in which a molecule diffuses freely here and eventually arrives here. By changing the speed, by changing different magnitudes, experimental parameters, you can get, for example, the diffusion of this molecule. You can get more complex problems. For example, you can get this pink curve in which you have two species that belong to the free species diffusing, but a second species that is absorbed, and the electrons now are not going with the molecule, but are hopping between these absorbed species. So the problem is complex, but now we can deal with that. Another way to look into this problem is to use more modern techniques. For example, fluorescent techniques that take a fluorescent probe and analyze for example, the movement of these fluorescent probes, the correlation, fluorescence correlation spectroscopy, fluorescence recovered after photobleaching, all these kind of techniques we applied, and we found interesting things. Here I will not go much into details, but you see a dye, a charged dye moving here, and what we observe is that at low ionic force, meaning low salts content, this is the time of residence of a molecule, meaning long time of residence means that the molecule is moving very slowly. And see here we vary systematically the pore and the neck diameter, and we find that the molecule is quite trapped. It's not moving a lot, it's quite slow, the movement. And it's not depending on the pore size. Why? Because the ionic force is low. So the electrostatics of the system keeps the molecule hanging on the wall. So the movement is very slow. When you increase the ionic force, you put more salt, you screen the charge from the pore surface, and now, for small pores, yes, molecules tend to stay into small pores, but as pores get larger, the molecule residence times are lower, so the molecule goes faster. So here you see two regimes. One regime which is electrostatic, and one regime which is, for example, determined by the size of the pores. So this gives you an idea. This is just one dye molecule traveling along pores. Two regimes in different salt concentrations. So whenever you are talking to sensors, easy. Fundamental things are yet to be understood. Let me finish the talk. Still have about, Mr. Chairman, about 20 minutes more, so no problem. The chairman didn't say no. Now, let me last 5 minutes about decoration. Just to show you, we can decorate with molecular groups, with polymers, with nanoparticles. You can decorate by adding molecules or by putting molecules in the solution, initial solution. This is one simple effect. We have a probe. We test that the red probe, which is a charged molecule, can cross this mesoporous material. We modify this with a phosphate of a long chain phosphate. This is a charged molecule. Now we made the same experiment, and we see that no signal is obtained. So we put here a steric hindrance to a charged molecule. We now have hydrophilic pores, and the molecule cannot go in. But when we use this other probe, ferrocene dimethanol, which is slightly hydrophobic, this molecule can go inside. So by just changing the molecules dangling from the pores, we can separate these molecules, detect them very easily, and kill and get these ones out. So this is interesting for molecule sorting. Which are the things we can do? We can do the same by attaching molecules with charge. Here is an amino propyl function dangling out from a silica surface, silica pores with an amino group. We see, for example, for this negatively charged probe at acidic pH, that this gives us a signal while a positively charged molecule does not. And this effect is reversed at high pH. Why does this happen? Because the charge of the surface switches. At low pH, we have these positively charged groups. This is neutral or positively charged. So this positively charged surface electrostatically repels a positively charged molecule and exchanges a negatively charged molecule. And of course, the process is reversed at high pH, in which this and this species are deprotonated and now the pore is negatively charged. So nice, we have an ion perm-selective membrane. It's not so good, it degrades, but interestingly, what we verified is that we could speciate which were the intervening species. It's a long story, so maybe I will stop here and leave you ask if you are interested. But we know which is the speciation of the surface, which is very essential. We combined all this into electrodes, combining the bottom-up approaches of making these mesoporous materials and modifying them with the people in electronics, our neighbors, the electronic guys, and made these artificial tones, right, that give us complex signals into these pattern patches. And let me finish by telling you this example on how can we program, how can we add a little more intelligence to our systems. We combine them, two different building blocks, the mesopores and then polymers. And we put polymers inside the mesopores. In this case, for example, let me tell you how can we grow polymetac. Polymetac is a positively charged polyelectrolyte We can attach polymerization trigger from the surface here. This was made in collaboration with Omar Azaroni in La Plata. And we can take advantage of the fact that we have a negatively charged surface to attract positively charged monomers. Then we make a 1,000-fold pre-concentration, and we make pair inside the pores. We have a positively charged polymer inside the pores. We recorded this, we saw that we lost porosity, we changed the pore size, everything was good. And we observed that, for example, this is the signal of positively and negatively charged molecules crossing or not the membrane. This is when we increase the size of the polymer. For small polymers, a positively charged, a positive or negatively charged molecule can go inside, but when we increase the polymer size, a negatively charged is pre-concentrated while the positively charged is not passing. It is passing a little bit, you will see how, but not passing. And this effect can be retrieved and is very reproducible. But what happened? Look, here we can separate negative from positive charges. So you have a positively charged polymer, a positively charged molecule will not enter, but here it entered a little bit. Of course, much less than this. What's happened? We don't know. We didn't know until we made the theory. We developed the theory to explain this with Ivan Sleifer and Mario De Casucci in Northwestern University. They could have an exact model taking into account a very complex system in which we have a polymer, a polyelectrolyte, a charged surface. The polymer can go lean on the surface or be upwards depending on various conditions, and this is a second phase. So if this phase is negative, even positively charged molecules can go inside complex and make their way in. So the systems are really, really, really complex, but we are understanding how. Just a couple of examples to close. This is very nice. We put a phosphate polymer, and what happens with this polymer? It's a barrier towards negatively charged molecules at neutral pH. Why? Because it's phosphate. It gets ionized. So the pore is negative, and molecules, negatively charged probes, do not cross the pore. But when we add calcium at neutral or alkaline pH, suddenly molecules pass. Why? Because calcium neutralizes the phosphate here, the polymer collapses and it opens. What's this? This is a kind of membrane that is calcium activated. You add calcium, the polymer reacts with calcium, opens the door, and now the door is open for molecules to pass. This effect is reversible. This is interesting because it's like a biopore, but made with a ceramic underpolymer. And this is my last example. This is, you can put a thermoresponsive polymer here. NIPAM is a very well-known polymer. We can put it on top of the surface and not inside the pore using another strategy. And what happens here? At a low temperature, NIPAM is halophilic. So it makes a kind of microgel on the surface and blocks the pores because it's a microgel. Molecules will not go in. It's too dense, too thick. But at a higher temperature, this NIPAM gets hydrophobic, expels water, collapses, and opens the pore. So it's a temperature signal. But which molecule is going to pass? The molecule in which we permit to pass, because we can tune the chemistry here inside. If this pore is negative, only the positively charged molecules will enter, and the negatively charged will be repelled. So what's this? This is a combination. This is an AND door. If the temperature is higher than this and your pore is negatively charged, only the positive will pass. You can code whatever you want. Now we are writing code for materials. We are telling the material, do this and this. And this is what I find interesting. Of course, we can make more complex things, but I think it's done. We made very strange things I wanted to tell you. But we can, of course, I showed you a lot of examples in the film field, but we're also doing this particle, for example. It's a particle that can get excited here because it's a gold particle that can get heat by irradiating with light. Then we know how to transfer the rate of transfer of heat to this polymer. This is a responsive polymer, so these particles can change size and the hydrophilicity with an optical requirement, etc. What I would like to take home is that we can use a variety of nano building blocks. I talked today about mesoporous architectures, combining them with molecules, with polymers, with biomolecules, to create really complex systems that can respond to external stimuli, and that are, I hope, more near to living systems than things were done before. So thank you very much for your attention, and thank all the people in my group and my former group and my collaborators for having helped me in developing this field. Thank you very much.
Thank you. Beautiful presentation. Could we have some questions, discussion? Yes.
Very nice presentation. I want to come back to the mycels formation and the fact that they are getting into an organized form. And is it dependent on the type of molecules that you were using, like CTAB or no? Because if you had used, for instance, the PPO, the polymer, the copolymer, plurally, would you obtain the same thing? Because then you would just apply the mycels. So I was wondering the impact of the charges.
Yes, very, very interesting question. In fact, what you work with there is by selecting the molecule and selecting, for example, a polymer, if it's a block copolymer of PEO and PPO, or PEO and polystyrene, for example, what you are working on is in the relative volume of the head and the tail to see the shape, and then, of course, the head and the tail, the hydrophilic balance, in order to see which is, for example, the best solvent to use, the best solvent after evaporation, and to, of course, tune the hydrophilicity of the building blocks with the polymer. So there is a lot of study I didn't show about how the very existence of the inorganic species, which are hydrophilic or not, affect, for example, the phase diagram of this surfactant. So, in principle, you can use a lot of different surfactants. There are many used in the literature in different situations, but you have to study the system previously. And of course, most of the work we did here was with non-ionic polymers, which is easier because you don't have the effect of charges, which is quite more complex. But if you're interested, we can discuss privately.
Very nice talk. So I just have a question. Have you studied the hydrophobic interactions in your system?
Hydrophobic between
polymer and molecules which are sensing benzene?
Well, we are on it because we were more interested for the moment in studying the difference in very hydrophobic systems, for example, in molecules inside the pores that are hydrophobic, with hydrophobic pores as a pre-concentrator.
Yeah.
Okay. And then we made a lot of work because charged probes are easier to get in electrochemistry, and it was easier, it was not, it was very complex. So we made an in-depth study of charged probes. We didn't work a lot with hydrophobic probes, but we're also working with hydrophobic probes, and I don't have the results here, but are comparable. But they are more complex,
Yeah.
much more complex. Because of the electrochemistry, much more complex. They can polymerize, they can make some species, yes.
Thank you.
Interesting question, thank you.
What about the transport of larger molecules, larger than solvent or calcium ions, transporting the pores? Is that interesting?
Yes, that's a very, very important question. It depends a lot on which is, let's say, the entropy loss or gain of these molecules. It's not just about size. You can have, for example, we tried with enzymes. Enzymes tend to have a very boring behavior. Not boring, but they tend to absorb and then block the pores due to the size. Depending on the pore size, you can make them advance a little bit. But they are difficult to open. On the contrary, there are some studies in, for example, polymers like polyethylene glycol or other polymers that open and reptate, but they have an entropic penalty there. So, but there are studies on that. And
so they're denatured?
They denature, they open, they reptate, and they advance. But this was another interesting system. Is what happens with biomolecules. Many interesting biomolecules, such as peptides, aptamers, or short DNA or RNA, for example. We wanted to put them. Absorption and desorption processes are quite interesting, and also transport. But we are not advancing that much because just very simple molecules have very complex behaviors, and we wanted to understand that if we're advancing. And we have qualitative results. Interesting.
Yes.
Thank you. I think you mentioned in the beginning that you had some results on confinement. Are you referring to quantum confinement, for example, in some light-emitting material that are porous materials, like, for example, porous silicon? It's likely because of quantum confinement.
Okay.
I don't know if you have some.
But that's a second one. It's nice. It's a good question. We all know electron confinement. And we all know, for example, if we make a wall very thin or nanostructured, we will have nanocrystallites. For example, in our case, we work a lot with titanium dioxide, cerium oxide, oxides that are nanocrystalline. And their properties depend on all the electronic properties. And the electronic properties also depend on the size of the crystal. There is the quantum confinement in the walls, because you have the electrons. But within a pore, you have solvent confinement, meaning that the thermodynamics is different, because you have a field now. You have a polarizable surface, and you have polarity, and you have a polar solvent that orients because there is a wall. And that leads to organization of the solvent and maybe a different partition function for the solvent. So this will confine the solvent inside. It's not an electron confinement, it's solvent confinement, what I was referring to. But of course, you can get more complex systems because when you transfer an electron to a molecule that is inside, you should also take into account where it is, what are the walls doing, and if you have metallic particles inside, you have also very interesting electron confinement effects due to the proximity of semiconductor walls. You have kind of nano junctions.
Could I ask you, in the same line, is the plasmonic?
Are your plasmonic nanostructures in regular order in your pores?
We were not able to do very nice ordered plasmonic structures. However, what we observe here is that when we produce nanoparticles inside this, like a ship in a bottle, we first produce small particles, and then we see a shift in this peak, and we modeled this system, and what's happening is that we begin always to create small particles, but then to populate our pores. And whenever the distances become close, you have a change in the plasmon due to the proximity of a second particle. We use that as a measurement of the pore filling and the average distance between the particles. There is an effect, a collaborative effect, in some regimes.
Thank you. Yes.
Hi, thank you for a very nice talk. I have curiosity in the core shell nanostructure that you have with the ball. Have you tried different thick of the silicium oxide? I think it's one of the last one, maybe this one. Because how the thermal effect is affected with the thick of the shell? Because
Beautiful one, thank you.
yeah.
No, what we did was a little more complex. We measure the thermal conductivity of mesoporous films in this way. We deposited nanoparticles inside films or in a surface. We irradiated with a laser in the 980. This excites the internal transition of electrons in the metal. It's not a plasmon. It's very precise. It excites just the inner electrons. And then here, at a given distance, which is tailored by the film thickness, we deposited, this we did with Luis Diaz-Carlos in Aveiro, we deposited a molecular thermometer. It's a molecule in which the emission is very finely dependent on the temperature. So by working in dynamic systems, we could have a good idea of which were the thermal properties of this material. And then we adapted this thickness. The laws are not exactly the same in order to optimize the shell here, in order to let the heat flow from here to here. Yeah. It's a long work.
All right. Thank you very much. Let's thank our speakers. We'll take 2 or 3 minutes to set up for the next speaker, so please stretch your muscles, look at the waves.